Hello everybody. Today we are going to discuss further on the flip-flops. In our previous lecture we have understood a flip-flop is an edge triggered memory device that at the time of whenever clock transition is there and active clock transition is there, then the output can change. And how output will change, that depends on the type of flip flop. So for example, in our previous lecture we have seen D flip flops. In case of D flip flop, the output output will change as whatever is the input at the positive edge. So let's say this is my positive edge of the clock and D value, this is my clock, and D value is 1 here. So whenever this positive edge will come, the output Q would be reflected at after some this propagation delay. So after this propagation delay, whatever is the value of D, that would be reflected in the output. So this is the characteristic equation, or this is the output function for D flip flop. Similarly, there could be other different type of flip flops where output will change whenever there is a positive transition or negative transition or the active transition of the clock. At the active transition of the clock, the output Q or QR can change. Rest of the time, the output will have no impact at all. So the output will not change until next positive edge will come. So at this positive edge, again we will see what is the value of D. If the D value is 0 here, if D is 0, then the output will become 0, otherwise output will not change during one clock period. So similar to D flip flops, there are other type of D flip flop which we are going to discuss today. One of them is RS flip flop. So this RS flip flop is actually the fundamental flip flop, because similar to RS latch, this flip flop is also is kind of a very basic flip flop, and this is also fundamental because all other flip flops can be designed using RS flip flop. When we see in the production, basically the chips which are produced or flip flops which are used in different circuits, usually RS flip flop is the one which is rarely used because of some constraint that we'll discuss now, but otherwise this is fundamental because it's most easy to design, and all other can be derived using this. So let's quickly see what is the behavior of this RS flip flop. The behavior of the RS flip flop can be mentioned using this truth table. So if the value of R, S and Q is this, then we'll write what is the value of Q plus. So if it is 0 and 0, if the Q was 0, the output is also, next state is also going to be 0. If Q is 1, then next state is also going to be 1. So it depends on the previous state what is going to be the next state. However, if R is 0, S is 1, then output, it does not depend on the output, but Q plus is always going to be 1. Similarly, if R is 1, S is 0, it does not depend on the previous state, but output is always going to be 0. If both of them are 1, then this combination is a invalid combination, so that is the input we should not give. And essentially, because of this particular reason that R and S both cannot be 1, that combination does not is not valid in case of RS flip flop. That is the reason that these are not used in many of the circuits. Now let us see one of the implementation of RS flip flop. So RS flip flop can be designed using master slave combination. This is called master and this is called slave. This is called master because my original inputs are connected to master and whatever is the output of master is connected to slave. So because it is edge triggered and we have a clock signal here, so we give the inverted clock as an input to this. Inverted clock is used as a gate to the master flip flop. So this is this is S and this is R. Now the output of master flip flop, master latch is given as a input to the slave latch, and it is gated with the original clock without inverted. Now let us say how it works. So let's consider this as a intermediate input P, and this is my final output Q. So let us consider that this is my clock signal, and this is value of R, this is S. So initially let us say R is 0 and S is 1. And then we can see the value of P as well as Q. So let us consider the at some point T which is slightly before the positive edge. So this is a time T1. So at time T1 the clock value is 0. So inverted clock value is going to be 1, and at that time my R is 0 and S is 1, correct. So at this time, because S is 1 and inverted clock is 1, this will become 1 and this will become 0, because this is 1, this is 0, set is 1, reset is 0. So Q will become 1 and Q dash will become 0. Clock is 0 at this time, this is 0 at this time. So my output is going to be the previous state, and let us assume the previous state is 0. So let us assume the previous state is 0. So we don't know. This is 0. So that means this is going to be 0, and we don't know what is the value here. So let us consider it as P was also 0. So now let us see what would happen at some time after this positive edge, at very small difference of time after positive edge. Let us consider what would happen. Let us consider this as T2. So at T2 my clock has become 1, and because it has become 1, the inverted clock has become 0, this became 0, this became 0, and now P value will be the previous value. So this Q1 will still remain 1, Q1 dash will still remain 0. Now the clock has become 1, this has become 1. So the value which is given as the input to slave set is 1, and slave reset is 0 because of this 0. Now because of that my Q is going to be 1. But when it will be 1? Only after clock has been there, and when this 1 will reach here. This 1 can reach only after clock has become 1. So after some small duration after clock has become 1, my output will become 1. So otherwise, because of this gate, this master latch will not change its value when clock is 0, and because of this gate the slave flip flop will not change its value when clock is 1. So the output will change only at the positive edge of the clock, and that's how this master slave combination will work like a RS flip flop. Now because of this combination, when R and S both are 1, the input combination is not allowed. This input combination is not allowed because both of these J and K flip flop, so both of these master flip flop, master latch and slave latch, they will not work correctly. So because of that my master slave RS flip flop will also not work correctly, and that's why we need to find some alternative method which could serve as a better flip flop. That is why JK flip flop is used. In case of JK flip flop, let's do it within this diagram only. So in case of JK flip flop, what do we do? JK flip flop is very similar to RS flip flop. The only thing is the input is J and K, you have Q, and the characteristic table is also somewhat different. In case of J and K, if J and K both the inputs are 0, Q plus the next state is same as whatever is the Q. If J is 0, K is 1, then the output is if J is 0 and K is 1, then the output is 0, and when J is 1, K is 0, sorry, this is K. When J is 1, K is 0, the output is 1. When both of them are 1, then the output is the inverted output of the previous state. So if we write the characteristic equation, for the characteristic equation it will become something like this, that next state depends on J Q dash plus K dash Q. And as far as implementation is concerned, so the implementation is very similar to my RS flip flop. The only difference is that I will now call this particular input as J and this I will call as K, and similarly I will use RS master latch and RS slave latch to make sure that this invalid combination does not occur. What would be done, that whatever is this input, the output, final output is given as a feedback loop to this input, and whatever is the final output here, that is given as a feedback loop to my master latch. This feedback loop makes sure that this 1-1 combination will result in the previous or the reverse of Q. So you see that J is given input as a Q dash and K is given as the input as Q. So because of that, your output will be the inverted one. Now there is another flip flop which is also quite commonly used, that's called T flip flop. So in case of a T flip flop, we use this particular idea of J and K. So let me erase this part. In case of a T flip flop, like D, there is only one input T and we have a clock as an input here. This is Q and this is Q bar. Now in case of a T flip flop, if T is 0 and then whatever is the previous value of Q, this will Q next state is going to be the if T is 0, then it is going to be same. If T is 0, the output is going to be Q, or can write it like this. But if T is 1, the output is going to be the inverted value of the previous state. sorry, this is 1 and this is 1, then this will be 0. So essentially my q plus is always going to be, if t is 0, then it is going to be equal to q, and if t is 1, then it is going to be inverted of q dash. So this can be written as the characteristic equation of my q dash. I can also write it as t XOR q. The implementation of this can be like, if I connect j and k as the inverted ones, then also we can design the T flip flops. Okay, so these T flip flops, we will see that they would be used in counters, and we'll see them in some of the next lectures. So these are the different type of flip flops. Most of the time we use D flip flop because they are most simple one and most effective to store the memory. But sometime, for example, for counters or for storing certain kind of combinations, T flip flops are also used, and JK flip flops are also used in some cases. Now, in addition to this general category, like different type of flip flop, there are also a couple of additional inputs which we should see that which could be applied in these flip flops. So one of the important one, you see that when we initialize this flip flop, how do we know that what should be the initial value? We always say that your flip flop, if your input, for example, if it is RS flip flop, if R and S both are 0, the output is whatever is the previous state. Now what is the previous state? We don't know. So because of that, an additional input to these flip flop has been designed, which is called clear or a reset. So let's say this is my R and S flip flop. So this is true for all other D flip flop also. Now there are two additional inputs, preset and clear, and this is Q, this is Q bar. Now these preset and clear are usually asynchronous inputs, so that means they does not depend on clock. So when the positive edge or negative edge of clock will come, it doesn't matter on them, but this preset and clear can initialize the inputs, initialize the outputs. So usually you will see that most of your hardware, they have a small reset pin. So in any of the hardware, you will see some, at least one reset pin, which reset pin will ensure that the starting operation is clear, so which will initialize all the memory elements to correct values. So and this reset pin has to be independent of clock, because after the clock will come into picture, clock will your next value will depend only on only at the certain point of the synchronization point. So that's why these preset and reset are usually asynchronous inputs, and whenever they are given, their value would be effective. So in another way, these preset and clear can change the functionality of my flip flop. So that is why it has to be, this care has to be taken that preset and clear values are only given at certain point, usually on in the initial ones. So and it's also sometime there that this is the inverted values, so that if it is inverted, then we can call it preset n or clear n. So what is going to be the behavior? Whenever clear is 0, it will make Q as 0, and whenever preset is 0, then it will make Q as 1. So this is the let's see it using a truth table. Let's write clock D preset N clear N, and this is the value of Q plus. So independent of this, if the value is actually both of them, if it is inverted value, both of them would be 1, that is not allowed. If clear is 1, so when preset is 0, so that because it is active low, so when preset is 0, the output is going to be 1, and similarly when clear is 0, that means clear is active, and then output is going to be 0. Similarly, if both of them are 1, then circuit will behave according to clock and T. So if D is 0, then output is going to be 0, and so this only happens at the positive edge. So at the positive edge, if D is 1, the output is going to be 1. So we must understand that this circle means active low. If the circle is not there, so we have to consider that, let's say if this active low signal was not there, in that case we can say this is only preset and N is not there, and this is only clear, N is not there, and then these circles are also not there. So we can reconstruct this. So we can say this circle is not there, and this is preset and clear. So in case of preset and clear, which is non negative edge, so that means in that case, if it is 0 0, then if it is 0 0, then then circuit will behave like a regular circuit. But if clear is 1, then output is going to be 0. If preset is 1, then output is going to be 1. When both of them are 1, it means it's a conflicting situation. This situation is not allowed. Only one of the preset or clear would be there as the input. So this would be a condition of not allowed. So this preset and clear are one of the additional input circuits which are also commonly used in some of the flip flops. Along with that, now let's consider one more scenario before finishing this lecture. So let's consider one more scenario. Now let's consider that we have this D flip flop. In case of a D flip flop, you know that whatever is the value of D, that would be reflected in the output. Let us say we don't want to do that. We want to say that D value should not be reflected with every change in the clock. So what should we do? This particular question is also coming because as the transitions are there, each transition consumes a lot of power. Now to avoid that, can we do something like if we want only during certain period of clocks, then we want this D to be transparent, otherwise we don't want. So then we can also gate this clock. So that means we can, so this is my regular D flip flop. I can create a gated D flip flop. So one of the idea of gated D flip flop could be something similar, like let's say I have this value of gate and I use this clock, and then I use this as an input to my regular clock. So this is a straightforward circuit. What this will ensure that if I don't want to use clock, or I don't want my flip-flop to change its value every time when clock is changing, then what I can do is I can use a gate. I can so in other words, what I am doing is I am redefining my clock. I am saying that I am using a new clock, which is a gated clock. So this gated clock is a very powerful mechanism to remove certain activity in the flip-flops whenever it is undesirable. Now this has certain disadvantage also. This particular implementation has certain disadvantage also, because what you are doing now, clock is otherwise used as a synchronization mechanism. Now you are redefining the clock. Because you are redefining the clock, this new clock, which is a gated clock, is shifted by one gate delay. So that means now, because it is shifted by one gate delay, it is not does not remain a global synchronization point. For different circuits there would be different synchronization point. The other thing is, let's say this gate behavior is this gate behavior is not synchronized with clock. So let's say I am doing this is my clock signal, and this is my gate signal. So gate signal is, let's say, want to avoid, so would like to do something like this, or there is also possibility that it does something like this. Now what would happen, this is my clock dash, or my new clock. In the new clock, what is happening now? First of all, it is not synchronized. You see, because of this, now even after this there would be a certain delay of this AND gate, and because of that my clock dash is even shifted. The other thing is, let's say, because of certain reason the clock has a flicker, this gate signal has a flicker, and because of that there would be multiple, there would be so there would be multiple positive edge which is created, and each positive edge can create some side effect. So that's why this particular mechanism where we gate the clock being the signal which is controlling everything, it's not a good idea. So what could be a better or an alternative arrangement? The alternative arrangement could be something like, instead of gating the clock, what we can do is we can do some sort of a chip enable signal. So this is some, like, we can create a D flip flop here, and let's say this was my original input D. Let's put it on the below side. So let's say this was the original input D, and now we have some other signal, like let's call it CE, chip enable. So this chip enable, if this is 0, then what it does is, whatever was the Q value, it take that as input. Here we are not changing the behavior of the clock, but if chip enable is 0, then whatever was the previous state, it will remain in that previous state. If chip enable is 1, then whatever is the value of D, that will go in the Q. So this could be sometime a better implementation, which can save some of the which can control that when D has to be applied to the to our D flip flop. So with this, let us close today's lecture, and we'll hope to do some more discussions or some more circuits based on these flip flop in forthcoming lectures. Thank you very much.